If you're wondering how freezing light could change the future of technology and physics, you've clicked on the right video. Light, once thought impossible to stop, has now been frozen, challenging everything we know about speed, time, and matter. This achievement opens the door to groundbreaking possibilities. Discover how freezing light might revolutionize quantum computing, redefine optical technology, and reveal new insights about time and reality, and how this discovery could reshape the boundaries between light, matter, and information in unbelievable ways. Imagine a beam of pure light, say from a flashlight or a laser pointer, shining through a dark room. Now imagine being able to reach out, grab that beam in midair and freeze it in place. It sounds like a scene from a science fiction story or a wizard's spell, doesn't it? For ages, such an act was only fantasy, a symbol of suspending time or wielding ultimate control over nature. Light, after all, is supposed to be the fastest thing in the universe, something so fleeting you can never catch it. Yet in a groundbreaking scientific achievement, researchers have found a way to do something astounding. They have effectively frozen light for the first time in history. This isn't freezing in the sense of turning down a thermostat. There's no block of ice encasing the light. Instead, freezing light means halting its movement, making it stand still or behave like a solid object rather than a racing beam. For generations, the idea of stopping light in its tracks was thought to be impossible. How could you ever grab a ray of sunshine or a laser flash and make it hold still? Light was always thought to be ethereal, not really touchable or holdable, certainly not solid. But very recently, in a remarkable experiment, scientists managed to make light hold its shape, like a solid and even flow like a liquid at the same time. They essentially created a new state of matter out of light, something completely mind-bending, a supersolid made of light. Think about what that means for a moment. We're talking about light. The illumination from the sun and lamps, the glow in a flashlight beam, behaving as if it were a piece of matter. In our everyday experience, light illuminates the world and travels in straight lines or bounces off mirrors. It doesn't just stop and pile up like snow, and it certainly doesn't form crystals that you can touch. The notion that light could be solidified in any way challenges our common understanding of reality. It's as if you took a beam from a flashlight and it suddenly stood frozen in mid-air, glowing and suspended like a neon rod you could walk around and inspect. It raises all sorts of questions about what light really is and what the fundamental rules of physics allow. So, how did scientists manage to do something so seemingly magical? How do you freeze something that's always moving at incredible speed? To answer that, we need to journey into some of the coolest corners of physics, quite literally, into realms of extremely low temperature, and into the strange world of quantum mechanics, where the normal rules of nature can bend in surprising ways. This story involves exotic states of matter, cutting-edge technology, and imagination-stretching concepts that sound like they belong in science fiction. But rest assured, this is real science happening right now, and the implications are huge. Our journey begins with understanding why freezing light is considered such a breakthrough. If you told a friend that scientists have made light stand still, the first reaction would likely be disbelief. Light doesn't do that. Light is energy, not something you can hold. And that reaction is perfectly reasonable under ordinary circumstances. To appreciate the breakthrough, we have to recognize how extraordinary light itself is, and how clever the scientists were in finding a loophole that lets them pin down something that, by its nature, always wants to race away. Let's start by looking at what makes light so special, and why, until now, it has always been impossible to freeze light in place. Light is no ordinary substance. In fact, many people would argue it's not a substance at all. It's a form of energy that travels in waves, and it is always in motion. From the moment a photon, which is what we call a particle of light, is created, it zips away at about 300,000 kilometers per second, or roughly 186,000 miles per second. That speed, the speed of light, is like a cosmic speed limit. According to Albert Einstein's theory of relativity, nothing with mass can ever reach that speed, and anything without mass, like light itself, has no choice but to travel at that speed as long as it's in a vacuum. In empty space, a photon never slows down, never stops, and never rests. It's literally impossible under normal conditions for light to just sit still. For centuries, scientists struggled to measure light speed. Galileo's 1600s experiment failed due to light's incredible velocity. In 1676, Euler Romer proved light, has a finite speed by observing Jupiter's moons. By the 19th century, advanced experiments finally measured light's astonishing pace, confirming it's unimaginably fast and difficult to stop. If you could somehow chase alongside a beam of light, you would encounter some of the strangest effects of physics. Einstein later pointed out that from light's own perspective, time itself would effectively stand still. A photon that leaves a distant star and travels across the cosmos for millions of years will reach us as if no time has passed for that photon. Light, in essence, does not experience time the way we do because it's always traveling so fast that the normal passage of time doesn't apply to it. These facts are why the idea of freezing light sounds so unbelievable. Stopping light means forcing something that normally moves perpetually to come to a standstill. It's like trying to stop the wind with your bare hands, or halting a rushing river in its tracks. We can easily stop objects that have mass. You can hold a ball in your hand or park a car, because those objects can be at rest. But you can't scoop up a flashlight beam into a container. It will just slip away, because it isn't made of matter that can stay put. If you turn off the flashlight, the light doesn't freeze in mid-air, it vanishes, because the photons either hit something and get absorbed, or they fly off into space. One fundamental challenge presents itself. How do you trap something that inherently refuses to be trapped? How do you make light, which by its nature is always racing around, pause and gather in one place? Light slows slightly in water or glass due to refraction, but remains extremely fast. In the early 2000s, Lena Howe's team at Harvard slowed light to 17 meters per second using a bose-einstein condensate, an ultra-cold atomic cloud. They even momentarily stopped light, storing its information before releasing it. Scientists proved light could be paused by storing its information in matter. Lena Howe's 2000s experiment stopped light briefly, and by 2013, German researchers extended this to a full minute using a crystal. Though not literally frozen, light's information was held temporarily, demonstrating that light could indeed be tamed. Scientists advanced beyond slowing light by transforming it into a steady state, making it behave like matter. They achieved this by creating polaritons, quasi-particles formed when photons strongly interact with a material's excitons. Polaritons move slower, interact with each other, and behave more like matter, enabling light to crystallize. Over the past couple of decades, physicists have gotten better and better at creating and manipulating polaritons. They have even observed them behaving like a fluid under certain conditions, something often referred to as liquid light. For instance, polaritons in special materials have been seen flowing around obstacles and merging with each other without viscosity, much like a superfluid, a liquid that flows without friction. These were exciting hints that under very special circumstances, light might not always act like the untouchable, always moving beam we know. Perhaps it could condense, form droplets, or show collective behavior similar to that of matter. Scientists aim to create a supersolid from light, combining crystal-like order with fluid motion. Though theorized for 50 years, evidence of supersolidity remained elusive. In 2017, researchers formed atomic supersolids, but creating one from light was a holy grail. Finally, in 2025, an Italian team achieved this groundbreaking feat. That breakthrough came in late 2024 and early 2025, when a team of scientists in Italy put all the pieces together and actually managed to freeze light in a tangible way. Picture a cutting-edge laboratory where a table is lined with lasers, mirrors, and a tiny chilled device that looks unassuming but holds the key to trapping light. The heart of their setup was a small semiconductor chip made of gallium arsenide, a material well known for use in electronics and optics, with a bit of aluminum mixed in to fine-tune its properties. On this chip, the researchers had crafted a special structure, essentially a photonic crystal with a pattern of microscopic grooves and ridges. You can think of this structure as a kind of tiny optical maze or trap for the light, designed to corral photons in just the right way. The chip was cooled to extremely low temperatures to reduce any random thermal motion that could disrupt the delicate quantum state. In this frigid, controlled environment, the scientists directed an intense laser beam onto the chip. The laser was the source of the photons, a stream of light particles pouring into the semiconductor. As the photons entered the patterned crystal structure, they didn't just zip through it like light through a window. Instead, they interacted strongly with the material. essentially getting tangled up with the electrons in the semiconductor. Through this interaction, each photon effectively became a polariton, a hybrid light-matter quasi-particle inside the chip. In simple terms, the light was forced to slow down and take on some characteristics of matter within that crystal structure. You can imagine the photons entering this tiny maze and getting bogged down, as if a crowd of sprinting runners suddenly hit a patch of mud. The mud in this case is the interaction with the semiconductor's electrons, which causes the photons to drag and mingle with matter. At first, when the laser power was low, the photons, now in the form of polaritons, settled into a relatively uniform cloud within the chip. They all condensed together in one place, forming what's called a bose-einstein condensate. Basically, they were overlapping and coexisting as one giant quantum wave, distributed in the chip, but without any particular structure, like a blob of light. Achieving a polariton bose-einstein condensate itself was a feat. Researchers had done similar condensate formations in such chips before, proving that the light particles can act as one collective entity. But the real magic happened as the team increased the number of photons by turning up the laser power. As more and more polaritons crowded into the chip, this single blob of light started to change its form. It's akin to putting more water into a container. Eventually it might overflow or form droplets. In the case of the light, when the density reached a critical point, the uniform glow reorganized itself into a new pattern. The polaritons began to distribute into multiple pockets within the chip structure. Instead of one big ball of light, there were now two distinct bright spots or droplets of light within the cavity, separated by a small distance. In effect, the light had crystallized into a pattern, much like how water might crystallize into ice with a particular arrangement. These two bright regions of polaritons were like two peaks in an egg carton shape, and this pattern remained stable as long as the laser kept feeding the system. Crucially, these two blobs of light were not independent. They were part of one connected quantum state, like two lumps in a single wave of light spanning the chip. This was the telltale sign of a supersolid structure. The light had an internal spatial order, two distinct locations of higher density, somewhat like the beginning of a crystal lattice. Yet it was all one fluid, with the polaritons flowing and sharing the same quantum phase across both locations. A researcher described the state as a fluid of quantum droplets in a crystal pattern. Measurements confirmed the light formed distinct bright spots, behaving as a supersolid. Interferometry revealed these regions were phase-locked, creating a coherent wave demonstrating both structured order and fluid-like unity, hallmarks of a true light supersolid. When the scientists realized what they had in front of them, it must have been an exhilarating moment. A phenomenon that had never been seen with light before was now evident in their data. They had successfully frozen light into a supersolid state. The beam of light from their laser, usually something that would just pass through and spread out, was now trapped, standing in place in a peculiar frozen yet fluid form. It wasn't solid in the everyday sense. You couldn't pick it up or knock on it, but it had some structure like a solid, and it stayed put as long as the conditions were maintained. In practical terms, the photons had been coaxed into a kind of quantum ballet. They held a formation like dancers frozen in a pose. But that formation was sustained by ongoing motion and coherence, like dancers all still subtly moving in sync. It's a mind-bending thing to picture, a lump of pure light hanging out in one place, not zooming away thanks to quantum physics. The research team, led by Dr. Daniele Sanvito, and colleagues at the CNR Nanotech Institute in Italy, along with collaborators from the University of Pavia, the University of Trento, and even Princeton University in the US, announced their results in March 2025. They published the findings in the journal Nature, one of the most prestigious scientific journals, underscoring how significant this milestone is. In their report, they emphasized that this achievement is just the beginning of exploring supersolid light. They did something truly groundbreaking, but it also opens up many new questions. Now that we know light can do this, what else can we learn or make it do? Creating a supersolid from light introduces a new state of matter, blending solid structure with superfluid flow. This achievement blurs the line between matter and energy, demonstrating Einstein's E equals mc squared in action. It highlights how quantum physics defies conventional boundaries, merging seemingly opposite behaviors under extreme conditions. Supersolid light could revolutionize quantum computing by enabling stable qubits that interact efficiently. Normally, photons move too fast and don't interact, making entanglement difficult. However, in a supersolid state, photons behave collectively, allowing for long-lasting quantum memory and potentially enabling complex logic operations, paving the way for future quantum technologies. Beyond computing, consider optical technology in general. Today's high-speed communication networks use light traveling through fiber optics to send data, but the data is usually switched and stored using electronics, which are slower. If we could develop light-based circuitry that can not only shuttle photons around, but also hold them in place and release them on demand, we might create ultra-fast optical memory buffers or new types of signal processors that operate at the speed of light with very low energy loss. Supersolid light might be the kind of medium that allows for optical transistors, devices that use light to control light essentially, since the photons in the supersolid are interacting. Imagine a future photonic chip where information is encoded in light, and that light can be temporarily frozen in tiny supersolid pixels and then resumed. It could make data processing and signal routing blindingly fast. There's also a whimsical connection to science fiction, the idea of a lightsaber, a solid blade of light. Of course, what the researchers have created is not something you can swish around. It exists only within a special crystal and under special conditions. But just the fact that we can talk about light forming something solid-ish is remarkable. It shows that the gap between science fiction and science fact can sometimes narrow. We're not about to have actual lightsabers, since there's no practical way to make light stay in a sword shape in open air at room temperature with current technology. But experiments like this make one wonder what might be possible in the far future as we learn to manipulate light and matter ever more cleverly. On a more immediate scientific level, having this new platform of solid light gives researchers a way to probe fundamental physics questions. They can study how supersolidity works in a system that's quite different from the atomic supersolids. This could reveal new insights into symmetry and coherence in quantum systems. It might even allow simulations of other complex phenomena. For example, some researchers might use a similar setup to simulate aspects of superconductivity or other collective quantum states by mathematically mapping those problems onto light in a photonic crystal. In essence, the discovery doesn't just answer one question: can light be a supersolid? It opens dozens of new ones. Does supersolid light support tiny sound-like vibrations, phonons, quantum sound waves, similar to ordinary solids? And what would those be like? How does it react to being jostled or to changes in temperature or laser input? Can we make more complex patterns, say a whole grid of light droplets, essentially an entire crystal lattice of light? The team's experiment created a simple two-droplet supersolid. Pushing it to a larger array is an exciting prospect. Freezing light hints at controlling time. Light carries moments, and by pausing photons, scientists effectively pause those moments. While not true time travel, delaying a light signal alters when information arrives. This challenges our perception of time, holding photons in limbo until researchers decide when to release them. There's a related concept emerging in physics called a time crystal, a structure that repeats in time the way an ordinary crystal repeats in space. It's different from what we've been talking about, but it also breaks conventional ideas. In a time crystal, a system can have a periodic change that continues without expending energy, sort of like a ticking clock that never runs down. Both time crystals and light supersolids show how new physics can force us to revise our intuitive separation of concepts. We're learning that under the umbrella of quantum physics, light can be matter, time can have structure, and things that seem impossible become achievable in carefully prepared conditions. It's important to note that none of this violates physics laws, rather, it exploits them. Einstein's relativity is not being flouted. When light was frozen in these experiments, it was no longer just free light in a vacuum, it was trapped light inside matter, so the rules for material particles apply. The photons gave up their individuality to become part of a collective quasi-particle that can slow down. It's a bit like a loophole. The speed of light limit refers to light in vacuum. Here, light isn't in vacuum and isn't purely itself. It's in a disguise that allows it to do things we don't normally see light do. That's the beauty of combining different realms of physics, optics, and condensed matter and quantum mechanics. You can find these loopholes where something classically impossible is achieved by quantum trickery. This achievement leaves us with tantalizing possibilities. If we can freeze light, what else might we freeze or transform in the future? Perhaps researchers will find ways to make other force carriers like electrons, which have mass, do similar tricks, or create hybrid states involving light and even more exotic matter. While a lot of this is speculative, today's speculation can become tomorrow's discovery. A century ago, the idea of controlling atoms to the point of making them all march in quantum lockstep, a bose-einstein condensate or halting light, would have sounded like fantasy. Yet here we are. Who's to say what the next 100 years will bring? What's certain is that the story of frozen light doesn't end with this one experiment. It's the opening chapter of a new line of research. Scientists will undoubtedly try to refine the process, maybe making the light super solid last longer, perhaps by finding ways to reduce losses so that the polaritons live longer. They might also try making larger super solid structures. Or they could explore different materials that allow the effect at higher temperatures, maybe even room temperature someday, which would be a huge leap for practical use. They will also tinker with how to control the supersolid state. Can they make the light blobs move or change pattern in a controlled way? That would be like having a little solid light machine that could perhaps switch between different configurations on demand. We could also expand on the relationship between energy and matter. This experiment really blurs that line, and it harkens back to Einstein's famous E=mc². A deeper dive could examine how energy turns into matter and vice versa. For example, how particle accelerators can literally create matter from light in high-energy collisions, or how inside stars, light in the form of gamma rays, generates particle-antiparticle pairs. By looking at those examples, we appreciate that under the right conditions, the difference between a particle of light and a particle of matter is not so clear-cut. We briefly mentioned superfluids and bose-einstein condensates. But what about superconductors, materials that conduct electricity with zero resistance, or quantum Hall fluids, where electrons in a flat layer behave in strange ways under a magnetic field? And recall the fluid of light we discussed. That's part of a broader trend of discovering new phases that break the conventional rules. Each of these topics, from superconductivity, which is already used in technology for MRI machines and maglev trains, to new forms of quantum matter like topological insulators, deserves its own story. They all tie back to the theme of how quantum physics produces incredibly counterintuitive, yet real phenomena that could reshape future technology. The key takeaway from the story of frozen light is that the boundaries of the impossible keep shifting. What was once a wild idea, light standing still, has been demonstrated in the laboratory. It encourages us to keep asking what if, and to stay curious. Science is a continuous journey, and each breakthrough like this opens up many more questions than it answers. That's the beauty of it. There's always a next step, always a deeper mystery to probe or a new technology to invent. So perhaps in the near future we'll be discussing how scientists bend time or entangle entire systems, or how the quantum world can be harnessed to do things we once thought were magic. The saga of freezing light is just one chapter in that larger story. It leaves us with a sense of wonder and excitement for what comes next. After all, when even light, the fastest, most untouchable thing we know, can be paused and given form, it reminds us that we're just beginning to unlock the secrets of the universe. The coming years will surely bring more surprises that challenge our imagination and expand our understanding of reality. Perhaps one day we might even hold a small piece of solid light in our hands, an astonishing thought that shows just how far our reality can stretch. Got questions about frozen light and its future impact? Drop them in the comments. We'd love to hear your thoughts. Thank you for joining us on this journey through frozen light. Please like and share the video, and please do not forget to subscribe for more videos.